Okay, good morning again, guys. Last time we talked about exponential growth and decay, and we mentioned that exponential growth and decay models are actually born out of a nice type of differential equation. So specifically, these are the separable differential equations. So after working out some application problems with exponential growth and decay, we look at some general general examples of separable differential equations. So let's see what we did last time. Okay, we considered an equation like this, right? We say that an equation is a differential equation if it involves the derivative. So for instance, problem number 4 here involves the derivative, so it's a differential equation. And whenever solving a differential equation, we are looking for all functions y that satisfies this differential equation. So if you can think of a function y, and you take y prime, and if it happens that the answer is e to the x plus y, then that is a solution of the differential equation. So that's one thing to remember. The final answer for differential equations are not just numbers, as what we are used to in calculus, in pre-calculus or algebra. The solutions to differential equations are functions, and we stop our solution once derivatives and integrals are all gone. So we are talking about separable differential equations in particular in calculus 2, because I guess they are the easiest ones to solve, because the key is try to separate the variables. I mean, all those with a variable y to one side and all those with a variable x on the other. And that's what we did in the first two lines here. So I just used Leibniz notation to write y prime in terms of the ratio of differentials so that we can separate them. I also started the separation on the right-hand side, and then you do your cross multiplication or multiplication and division of both sides to essentially get this form, in which all those with a variable y are on the left and those with a variable x are on the right. So that means, indeed, we have a separable differential equation. And the nice thing about separable differential equations is that we can integrate both sides of the equation to get rid of the differentials, right? So we integrate, carry out the integration, and we will eventually end up with this type of solution. So all derivatives are gone, all integrals are gone, so I'm sure this is a nice form for my final answer. And we see here that if your function satisfies this, then it will also satisfy the differential equation. And you see that this solution is not just a single function, but it is an infinite family of functions, because you can give any value for c, and still you get a solution. And that's why we call such a solution a general solution, because this gives us a representation for all possible solutions to the DE, right? So you can't just put in an arbitrary value for C, then that's also a solution, right? In some applications or some problems, you might be interested to just one of these solutions. So basically, that's what we call a particular solution, wherein we don't want the entire family, but just one element of that family. So, and that depends on some initial or boundary condition. So I guess that's what we started with last time. So I have a DE here, oops. And we are given an initial or a boundary condition. Basically, this is telling us what is the behavior of the function that we want at the particular value for x. So in this particular case, this tells us that when x is 0, then y must be equal to 5. And I will use this information later in order to find what is the value for c that will give me the particular solution. So if you remember, we went through this process last time. I separated the variables. Once the variables are separated, I integrated both sides of the equation. And I came up with this general solution. This is, again, a general solution because A stands for any constant that you can think of, right? So, but since we are given an initial condition, y of 0 is equal to 5, then I need a particular solution, meaning I need to find what specific value of a will work, such that y of 0 is equal to 5. And essentially, we found out that a is equal to 5, and hence we get this particular solution. Okay, so do you guys have any problem with the separable differential equations? I'm thinking to answer just one example today, and then we'll move on to improper integrals. But let me know if you have some particular differential equations in mind to solve. I'll give you 30 seconds to send your questions. If not, I'll just pick a random problem from worksheet 5. Okay, no specific problem. So let's try problem 12 from worksheet number 5. Okay, so problem number 12 asks us to solve this differential equation, y prime equals y squared plus 1 all over xy plus y. We are not given any initial or boundary conditions, so we are looking for a general solution here. Again, write the derivative in terms of the Leibniz notation, because that will be that is the form that we want for the separation. And then let's start the separation also on the right side. Look at the denominator. In the first term there, x and y are mixed together. So I'll try to factor one of them out. But if you look at the second term, it has a y. So I can factor out the common y in the denominator and have y times x plus 1, which is good, because now I can manipulate this equation to have this separated form. I'll have y over y squared plus 1 dy equals dx over x plus 1. Good. And then since we are done separating the variables, then we can integrate both sides. Of our equation. There we go. But in integrating, I think I need to use u substitution in both sides. So let me do that here on the side. So for the left-hand side, I will let the u to be equal to y squared plus 1. That gives me du equals 2y dy. Or equivalently, that means du over 2 is the replacement for y dy. Okay. So the the left side will become 1 over u times dy over y dy will be replaced by du over 2, right? And then for the right-hand side, I will let w be equal to x plus 1. So that means dw is equal to dx, right? So I'll have dx over w on the right-hand side. And then now we can carry out the integration of both sides. So the integral on the left can be reduced to 1/2 ln of the absolute value of c. Supposedly there's an arbitrary constant c over there, but I'll worry about that later. And then the right-hand side is ln of the absolute value of w, and then I'll have the arbitrary constant c. And this is a usual thing for brevity of notations. We usually just use one arbitrary constant, but this arbitrary constant c here stands for the constant on the coming from the integration on the left, plus the constant, minus the constant coming from the right side. So we just lump them together into one big arbitrary constant c. That's why you only see one arbitrary constant here, but they are the difference of the arbitrary constants coming from the two integrals, right? And then let's revert to the original variables. I'll have 1/2 ln supposedly of absolute value of y squared plus 1. But I'm sure that y squared plus 1 is always positive, so I can get rid of the absolute value symbols and just use a common parentheses instead. But if you don't want to analyze it more, then you can just leave the absolute value there. That's a safe bet. And then on the right-hand side, I'll have ln. W stands for x plus 1. Oh, in this case, I cannot get rid of the absolute value symbols because x plus 1 might be negative at times. So to remove that possibility, I'll enclose it in absolute value bars plus the arbitrary constant c. And you see here, there are no derivatives involved. There are no integrals involved anymore. So unless you were told to solve for y explicitly, then this would be a nice final answer. And I think in some of the multiple choice problems, you are not really required to write y explicitly in terms of x, especially for transcendental or complicated functions such as this one. But I guess if it's just a simple algebraic function, then it might be helpful to write y in terms of x explicitly. All right. Any questions about this? Do you agree with Fatuma that this sounds straightforward? Okay, I'll take that as a yes. I hope that's a yes of type 1. You know, you understand it clearly, no questions at all, and not a type 2 silence, which is basically you don't get anything, so you cannot formulate any sensible question. So I hope it's type 1. And I want to tackle this at least 3 examples for this because if I remember it right, you just watched a video of it and you were not able to discuss it in the lecture. So hopefully this few examples help. Let me know if you have some questions about it. I learned that there is at least one problem about differential equations in the written homework. Somebody asked me about that from my other class, but do you guys, sorry, do you guys were you able to solve it without any difficulty?
I don't think I got there yet, but I'll let you know. I don't know yet.
Okay, yeah, sure, no problem. Yeah, and as you have said, this looks pretty straightforward, but I guess one cause of difficulty here would be on the separation. So in order to separate the variables, you need to recall some probably loss of logarithms, loss of exponents, factoring techniques, some identities if you have some trig functions in there. So, but I don't think you'll be given very complicated ones, but at least remember these basic topics from pre-calculus or algebra. Because after you have separated the variables, then it's just straightforward integration. You might use u sub, you might use some of those formulas for inverse trig functions, but that's it. And those are things that you have learned either in Cal 1 or in the first part of Cal 2. Okay. So if there are no other questions about this, then let's look at improper integrals. Oh, by the way, if you have some questions about the practice test or some of the homeworks, feel free to send them via the chat, and I'll try to insert them somewhere in our discussion today. So, and I hope you guys are at least preparing or in the middle of your preparations for test number 2. How is it going?
Good so far, but
That's nice to hear.
I think the only problem that I've had so far is with like going back for like 7.2 and 7.3, but the rest is good.
Okay, sure, yeah. So usually it's the first few topics are actually the hardest to review because it was a couple of actually it's almost a month since we talk about them. Okay. Yeah, I understand that, Christina. Yeah, it's a bit stressful nowadays, especially if you're still dealing with the aftermath of the winter storms. But yeah, hopefully you guys are now doing better than last week. So, okay, let's move on to improper integrals. This is in worksheet number 6. Again, these are some problems that I just lifted from the textbook. I didn't know, but in my version here, I lost my the title that I inserted and the disclaimer that these were just lifted from the calculus textbook. So I'm not claiming authorship of these problems. But anyway, let's work with them. So improper integrals. So what makes an integral improper? So if you have an integral from a to b of f of x dx, this becomes improper if either, number one, f is discontinuous at some number in AB, right? So if you look at the integrand, and you notice that that integrand is discontinuous at some number in the closed interval AB, then automatically it is improper, right? And the other possibility is that either bound is infinite. And I guess the second condition is much easier to spot, because once you look at the bounds, if at least one of them is infinity, then it's automatically improper, right? So, and then if your integral is improper, what we do is to transform it into a limit problem. I mean, what we try to do is to first identify what's the cost of impropriety, if we can call it such in such a manner. But look at the number that causes the integral to be improper, and we replace it by a variable, and then take the limit of that new variable as it approaches the number that we replaced, and then evaluate that limit. I know that's a lot of mumbo jumbo, but let me show you what happens through an example later. But we say that essentially what we try to do is to turn the integral into a limit, or into a limit problem. Then if the limit exists, then we say that the improper integral is convergent. Then the improper integral is convergent. Right. So essentially, you turn the integration problem into a limit problem. If you get a finite answer for that limit, then we say that the improper integral is convergent. Otherwise, it is divergent. So if you get an infinite limit, or if the limit doesn't exist, then automatically the integral is divergent, right? So essentially, if you get a finite answer, a finite number for your improper integral, it is automatically convergent. All other cases means it is divergent, okay? So let's look at some examples so that I can explain what do we mean by turning the integral into a limit problem. Let's try problem number 6. You can also let me know if you have some suggestions on what problems to solve for this. I have worksheet number 6. There are 30 problems in here. So let me know if you find some of these interesting so we can answer them. Or if you have encountered something from the quiz or from the homework that you think would be difficult or complicated, then just let me know. But otherwise, I'll just pick random problems from here, or not just random, but some of the interesting problems from my point of view from the worksheet. Okay, so let's start with problem 6, and I hope this is simple. We'll have the integral from 2 to 6 of dx over root of x minus 2. I really love to start with easy problems first so that I can explain the process to you guys, and then let's go to the more difficult ones towards the end, once you get the hang of the strategy, the solution strategy. Okay. Now, let's see. The instruction here is to first determine if each integral is improper. Then if it is improper, then we need to state why and rewrite it as a proper limit and then solve. Okay, so first we notice that the integrand is 1 over root of x minus 2, and that's sort of a rational function which will be divergent, which will be discontinuous when the denominator is equal to 0. And if you look at the denominator will be equal to 0 when x is equal to 2. And unfortunately, 2 is in the closed interval 2 to 6, right? So that means this is improper. Because the integrand is discontinuous at x equals 2. And x equals 2 is part of the integration interval, right? So since we have resolved that it is improper, and we know what causes the integral to be improper, so what we do is turn the integration problem into a limit problem, meaning we change the cause of the discontinuity into another variable. I'll call it, say, the variable a. You can use any other variable you want aside from x. So, and then until 6 of dx over root of x minus 2. And we take the limit as a approaches 2 coming from the right. Okay, so it's important. You turn it into a limit problem first, and then you make sure that you are approaching the cause of discontinuity from the proper direction. Here I am approaching 2 from the right. Why from the right? Because remember, the integration should occur from 2 to 6, right? So basically, we are only interested on the interval 2 to 6 because that's where we will perform the integration. And in particular, we want to approach 2 coming from the right. So these are our values for a. Because we don't care about what happens from the left of 2, because that is outside the integration interval. So we don't care if the limit will not exist coming from the left of 2, because that's outside of our universe, which happens to be the closed interval 2, 6 here. So essentially, you just need to take the limit as a approaches 2 coming from the right. Okay? So, okay, let me just leave that note there so that if you see the picture, you will be reminded how to determine if you are going from the left or going from the right. And then now we need to perform the integral here. But for that, I will let u to be equal to root of x minus 2. Oh, sorry, not root of x minus 2, because that will require a du that has a square root, which I don't want to happen. So the right substitution here is x equals 2. U equals x minus 2. Then du will be equal to dx. So essentially now we'll have the limit as a approaches 2 from the right of the integral of du over u to the 1/2. All right. But now, since I changed the variable from x to u, I should also change the bounds. And that's one of the drawback of this solution notation that I chose. I'll show you an alternative one later, but if you decided to do it straightforward like this, when you change the variables, you should also change the bounds. Okay, so that means if the lower bound for x is a, right? So if x is equal to a, then u will be equal to a minus 2. So the lower bound here would be a minus 2. And the upper bound is 6. So if x is equal to 6, then we need to know what's the value for u. And that value of u would be our upper limit. Okay, so here u will be equal to 6 minus 2. That's going to be 4. So the upper limit is 4. Okay, and then we can evaluate the integral now. So this would be the limit of this would remember this is basically u to the negative 1/2 du. So the integral would be u to the 1/2 all over 1/2 evaluated from a minus 2 to 4, and then we take the limit as a approaches 2 from the right. Okay. Then let me just rewrite it as 2 root of u evaluated from a minus 2 to 4 as a approaches 2 from the right. And since I was very careful here that when I change the variables to u, I also change the bounds, right? So I don't need to revert to the original variable anymore because, yeah, the bounds are given for u. So I'll simply use the fundamental theorem of calculus here and then plug the upper limit minus I'll plug the lower limit, okay, and take the limit as a approaches 2 from the right. The first term goes to 2. And then what happens when a approaches 2 coming from the right? Well, this guy will go to 0, right? And hopefully here you see that why it is important to take note of the direction. Because here, remember, if I take the limit as a approaches 2 from the left, the limit of the root of a minus 2 won't exist because there is no graph to the left of 2, right? So that's why if you forgot to write the direction for the limit, then the limit won't exist. But remember that we are just concerned with the behavior as a approaches 2 coming from the right. And hence this limit, or the limit corresponding to the second term, will exist and will just be equal to 0. Essentially here we'll have, I'll have 2 times 2, which is equal to 4. Yeah, Kevin, Christina is correct. What I did here for the new bounds is I just plug in x into the u substitution. Let me go here a little bit. Remember, I let u to be equal to x minus 2, and the lower bound here is x equals a. So when x is equal to a, I want to know what is the value for u. So in order to find a value of u, I just go back to the u sub and then plug in x equals a. So I have u equals a minus 2. Similarly, the upper bound here is x equals 6. So that means when x is equal to 6, I want to know what's the value of u. But we know that u is equal to x, which in our case is equal to 6 minus 2, so we get 4. Okay? And the rest is the limiting process. All right? So I want you guys to pay, again, extra attention to the notations because the instructions here in the section exercises, and I guess also in some of your homeworks, you will be reminded to use the proper limit notation, right? So you first need to translate it to a limit problem, and remember to keep the limit symbol as long as the limiting variable is still present in your solution. You only stop writing the limit symbol once all the variables a are gone. Okay. So let's try another one. Probably let's try problem 23. Problem 23 is the integral from 0 to 4 of e to the root x over root x dx. Okay, so here this is improper because the integrand is discontinuous at x equals 0, which happens to be in the interval of integration, right? So it's an improper integral. So whenever solving improper integrals, we need to write it as a limit first, right? So this would be equal to the limit of the integral. We replace the cause of discontinuity by another variable. Let's say a. 4 is fine because it's continuous other than at x equals 0. And then we take the limit as a approaches 0 coming from the right. Okay. Because again, we are only interested on the closed interval 0 to 4. And the only way we approach 0 on that interval is coming from the right. And then we'll have e to the root x over root x dx. And then if you don't want to change the bounds, because that might, the notations might pile up easily, right? So one thing you can do is to evaluate the improper integral instead. So note that you can start by solving the improper integral e to the root x over root x dx, so that you don't have to change the bounds. So here I can let u to be equal to root x. Du would be 1 over 2 root x dx. So that means 2 du is equal to dx over root x, right? So this indefinite integral can be rewritten as 2 e to the u du, right? And since I am writing a separate solution for the indefinite integral, so I don't need to change the bounds, right? I don't need to worry about the bounds right now. So, okay. And then I'll integrate this. I'll get 2 e to the u plus arbitrary constant c. And then I'll revert to the original variable. I'll have 2 e to the root x plus the arbitrary constant c. So I know what's the antiderivative of e to the root x over root x. So now I can go back to my improper integral. So here, I'll just copy it over. Okay. And then I know that the integral can be evaluated as 2 e to the root x evaluated from a to 4 as a approaches 0 from the right. And I know that these are the proper bounds still, because here the integral is with respect to x, and then the bounds here are with respect to x. So I am totally consistent with the bounds and the antiderivative here, okay? And you see here, I don't need to use those plugging in and so on, so my notations will not pile up. So I usually prefer this way rather than changing the bounds every step of the way, because this looks much neater than that. But anyway, so we need to evaluate this using the fundamental theorem. So I'll have 2 e to the root 4 minus e to the root a as a approaches 0 coming from the right. And then let's evaluate the limit. This guy is just e squared, right? And then this will just be e to the 0 because a approaches 0 coming from the right. So that's equal to 1. And so we'll have e squared minus 1 times the multiplier 2 outside earlier, and that's our final answer. And since this is finite, we have a finite value for the limit, so we say the improper integral converges. Okay. Did I mention that in the previous example? Let me see. Yes, I forgot to mention that here, hence the improper integral is convergent. Okay. Well, Christina, it depends on the question. If the question in the problem asks you whether the integral converges or not, then you have to write that final conclusion that the improper integral is convergent. If it's just asking what is the value, or if it asks you to evaluate the improper integral, then giving the number 2 times e squared minus 1 is fine, right? So just read the problem carefully about what is being asked. Okay, let's try another one. Okay, let's try problem 13. Problem 13, integral from -1 to 2 of 3 over x squared dx, right? And then look at the integrand. The integrand is a rational function. So we know rational functions are discontinuous when the denominator becomes 0. And the denominator here becomes 0 when x is equal to 0, which unfortunately is in the it's in the interval of integration, right? The interval of integration is from -1 to 2. 0 is in there, so that means it is improper. So let me just formalize that. The integral is improper because the integrand is discontinuous at x equals 0, which happens to be inside the closed interval -1 to 2. All right. And since it's an improper integral, we need to write this down as a limit. Okay. But the thing here is the cause of discontinuity is an interior point. And the trick here is to split the integral according to that cause of discontinuity as one of the limits, so that we can take the limit of those two integrals. So what I mean is, first I look at this as the integral from -1 to 0 of 3 over x squared dx plus 0 to 2 of 3 over x squared dx. Because if you see from our previous examples, we rely on taking the limit as one of the bounds, which happens to be the cause of discontinuity, approaches, as well. We rely on exchanging the upper one of the limits to a new variable and take the limit of that variable as x approaches the cause of discontinuity, right? So we want the cause of discontinuity to be one of the bounds. And that's the reason why I want 0 to be either a lower or an upper bound. But since 0 is in the middle, so that required me, is inside the interval, that required me to have two integrals here with 0 as a boundary. Okay? And then we use the limit notation here. I'll replace 0 by another name. For the first integral, I'll call it b, 3 over x squared dx. And here I want b to approach a 0 coming from the left. Because on the first integral, we are concerned with the interval -1 to 0. And the only way we can approach a 0 through that interval is approaching it coming from the left. Okay. Plus, here we have the limit of the integral from, say, a to 2 of 3 over x squared dx as a approaches 0, but this time coming from the right. Because here we are living on the closed interval 0 to 2, and the only way we can approach 0 is coming from the right. Okay? And unfortunately here we had two integrals to deal with, and there's no way to do it but to compute them separately. Okay? Now, but they have the same integrand. So basically I can do the indefinite integral first of 3 over x squared dx, compute it first, and then plug the answer into these limits. So here I know that this can be rewritten as 3x to the -2 dx. And the antiderivative would be 3x to the -1 over -1 plus c. So this is -3 over x plus the arbitrary constant c. Okay, so this is the antiderivative. Then let's go back to the limits here. So I'll start with the first limit over here. Let's evaluate that. Luckily, we already computed the antiderivative. It's -3 over x, and we need to evaluate it from -1 to b as b approaches 0 from the left. So as before, we plug in the upper limit, so we'll have -3 over b minus 3 over -1 as b approaches 0 from the left. Okay? And then let's see what happens to this limit. 3 over -1, that will just be -3. Okay, and then there's a negative outside, so expect a +3 in our final answer. But if you look at the first term, what happens here? We have 3 to the b, 3 over b. So 3 over b, b approaches 0 from the left. What happens if you have a 3 over 0? That goes to what? Do you guys still remember?
Is it undefined or like, well, no, infinity?
Yeah, it's infinity. If you're looking for the value of 3 over 0, it's undefined. But remember here, we're taking the limit as b approaches 0. So the denominator is not exactly 0, but a number that is very, very close to 0. And when we have that, that will be infinite, right? 3 divided by a very small number, that will be a very large number, right? But remember that b is approaching 0 from the left. So b actually stands for a number that is a very small negative number. So that means this is a negative number. Let me just rewrite that. 0, negative. So this would be negative infinity. But there's a negative in front, so this will be positive infinity, right? So that's negative of negative infinity minus minus 3. So that's going to be infinity plus 3, which is still infinite, okay? And that puts us in a very good position here, because even though we said that the first limit happens to be positive infinity, that makes this first term infinity. And the thing about improper integrals, if you split it up into two pieces, and one of those two pieces happens to be infinite, then automatically the integral diverges. So we don't need to compute for the other for the remaining limit over here, because it is sufficient to show that one of these two limits is infinite to conclude that the improper integral is divergent. So I can simply say here, the improper integral diverges. Okay, because one of the two pieces diverges, so it will definitely diverge. Okay. Lucky us, because we don't need to compute two limits over here. It turns out that one is divergent, so automatically the sum is divergent. Okay, is that good? We have time for one more example. Let me see which one would be good. Any questions, guys? Now you reverted to being quiet.
It's all good, all good. I think we just understand what's happening, so it's not that bad.
Okay, great. Nice to know. Let's see another one. Let me pick one good problem. Let's try problem 20. Or no, let me try problem 8 that has an arctan and that will result into an arctan. Probably you have seen this in the lecture, but just to emphasize the point, because this is one of the favorites for exams or quizzes. And then let's just consider some more complicated ones on Friday. But let's have this. Clearly, this is improper because one of the bounds is infinite, because the upper bound is infinite. So even though the integrand will be continuous everywhere, because there's no way the denominator of the integrand will be equal to 0, but the upper limit of our integral is infinite. So remember clause 2 of our definition for improper integrals. So if at least one of the bounds happens to be infinite, it is automatically improper. And as before, we just turned this into a limit problem. Okay. By replacing the cause of being improper, in this case, the infinite upper bound or upper limit, let's call it by another name. Let's disguise it as the number b. Same integrand, and take the limit as b approaches positive infinity. Okay. And then if you look at this, 2 over 1 plus x squared has antiderivative 2 arctan of x evaluated from 0 to b as b approaches positive infinity. All right. And then Let's plug in the upper and the lower bounds. So we'll have the limit of 2 arctan of b minus arctan of 0 as b approaches positive infinity. Let's go to the subtrahend first because that's easier. Arctan of 0. I hope you remember that this is nothing more but the angle whose tangent is equal to 0. Of course, restricted from negative pi over 2 to pi over 2. If you remember your unit circle, arctan will leave here. We're looking for when is the tangent equal to 0. Tangent will be 0 if sine is 0. And sine is 0 over here. And this is the 0 angle. So arctan of 0 is 0. Okay. And then for the minuend, we have arctan of b. But we know that we want b to approach infinity. So you can imagine this to be arctan of positive infinity, right? But what is arctan of positive infinity? Arctan of positive infinity is asking us what is the angle whose tangent becomes very, very large, right? So remember arctan, so we're looking for arctan of infinity is the angle theta such that tangent of theta is equal to positive infinity. I'm putting it in quotes because this is technically not correct because we know tangent only has finite values. Okay, but remember that tangent is sine theta over cosine theta. So basically, how do we get an infinity out of sine over cosine? Remember, we get infinity when the denominator becomes very, very small, right? So I'm looking for here a denominator is 0, and cosine is 0 when the numerator when sine is equal to 1. So yeah, Christina is correct. I'm looking for this. When is sine equal to 1 and when is cosine equal to 0? Luckily, that happens here at pi over 2, right? At pi over 2, sine is 1 and cosine is 0. So arctan of infinity happens to be pi over 2. So maybe you can include it in your list. Arctan of positive infinity is equal to pi over 2. And arctan of negative infinity is equal to negative pi over 2. Because in the latter's case, we're looking for when is sine negative 1 and when is cosine 0. That happens here at negative pi over 2. Okay. So basically, what have we learned here? We learned that this would be 2 times pi over 2 minus 0, and that would be equal to pi. Okay. And this is quite amazing because, and here goes again my nerdy side. Remember how we interpret integrals? We interpret the integral to be the area under a curve, right? And if you go quickly to a graphing software, 2 over 1 plus x squared has this graph. Something like this, okay? And the integral from 0 to positive infinity represents the area of this shaded region. And look at this. This is pretty much unbounded because we go to positive infinity. This shaded region goes on forever. But the interesting thing about it is that we have shown that this improper integral converges, and it converges to pi. So the area of this shaded region, though it runs until infinity, is just equal to pi, which is a finite number, right? So isn't that amazing? So get an unbounded region, an infinite region, and yet it has a finite value. Okay. Okay, maybe I can share a nicer story next time when we go to when we consider some more examples. But this is a nice. I find it very interesting to note that yeah, mathematics allow us to measure infinities of some sort, right? Infinite region having a finite area. And it turns out that that number is also an interesting number. It's pi. It's not just any number, it's pi. And we usually associate pi to be something that involves the area of a circle. But here we see there are no circles involved in here. but the area is equal to pi. So pi comes out in many applications other than computing areas of circles. That's why pi is pretty amazing. And whenever I have some some exams wherein I don't have time to answer a particular equation, and I have to guess what's the answer, my safe bets are 0, -1, 1, and pi. Those are my go-to guesses. And actually, pi becomes very relevant in almost all areas of math. That mathematicians celebrate Pi Day, which, by the way, will happen a couple of weeks from now on March 14. That's Pi Day. We celebrate it because it's 314, which is basically the approximation of pi to two decimal places. All right. But enough of my nerdy talk. So yeah. Oh, you get discounted pizza. Yeah, some establishments have that, and usually during the face-to-face days pre-COVID, the math department here at UH has this Pi Day celebration, wherein there are different types of pie, apple pie, pizza pie, and other pies available for free at the math office. But unfortunately, we cannot go to the math office anymore, so no free pies for us during this Pi Day. But okay, I guess that's it for now. On Friday, I hope that you guys bring with you some questions about the sections included in the second test that will happen this weekend. But I will also continue answering some improper integrals problem from worksheet number 6. So yeah, let's see each other again on Friday. Have a good day, everybody. Bye.